The next question I am going to take up is, we are given this determinant and we have to evaluate it and prove that 2 is less than equal to delta is less than equal to 4. So first of all we evaluate this determinant and then we will prove this result. So solution is, we are given this determinant and we have to evaluate it. So what we do is we expand this determinant by first row. What we do is 1 into its cofactor. The cofactors delete this row and this column. What we get is 1 sine theta minus sine theta 1. This place is 1 1. 1 plus 1 is 2, so we get a positive sign. And then we will have alternate plus minus sign. So this will be negative, minus sine theta into. Now delete this row and this column, we get minus sine theta minus 1 1, minus sine theta minus 1 and 1, and then this will be plus 1 into. Now this entry, so this row and this column will be deleted and we are left with minus sine theta 1 minus 1 minus sine theta, minus sine theta 1 minus 1 minus sine theta. Now we evaluate this. So this is 1 into 1, this into this minus this into this. So this is 1 plus sine square theta minus sine theta into this into this minus this into this into this is minus sine theta minus minus plus sine theta plus minus sine theta plus sine theta plus 1 into, now this into this is sine square theta minus this into this is minus minus plus 1. So we get sine square theta plus 1. So this is equal to, now this is 1 plus sine square theta. This is 0 and this is again 1 plus sine square theta. So we get 2 into 1 plus sine square theta. So now we have to prove that this lies between 2 and 4. This lies between 2 and 4. We have evaluated this determinant. The value of this determinant is 2 into 1 plus sine square theta. Now we have to prove that this lies between 2 and 4. That is 2 into 1 plus sine square theta lies between 2 and 4. Now we know mod of sine theta is always less than equal to 1. That is, the values of sine theta lie between minus 1 and 1. So sine square theta will lie between 0 and 1. So sine square theta. Now we know minus 1 is less than equal to sine theta is less than equal to 1. So sine square theta will be 0 will be less than equal to sine square theta is less than equal to 1. Square is always positive, and since mod of sine theta is less than equal to 1, therefore sine square theta will be less than equal to 1. So this is 0 is less than equal to sine square theta is less than equal to 1, and therefore we add 1 throughout. So this will be 1 plus 0 is 1 is less than equal to 1 plus sine square theta is less than equal to 1 plus 1. Now multiply this result by 2. What we get is 2 is less than equal to 2 into 1 plus sine square theta is less than equal to 2 into 2. That is 2 is less than equal to 2 into 1 plus sine square theta is less than equal to 4. That is 2 is less than equal to delta is less than equal to 4. So we have proved that this, that is delta, lies between 2 and 4. Now in order to prove that this lies between 2 and 4, what we do is we start with sine theta. We know that sine theta lies between -1 and 1. Then first step will be squaring. When we square it, square is always positive, and since the values lies between -1 and 1, so square will always lie between 0 and 1. So next step will be we will add 1 and then we will multiply by 2. First is sine theta, sine square theta, add 1, multiply by 2, and we arrive at 2 is less than equal to delta is less than equal to 4. Now there is one more question. Prove that the determinant of this is independent of theta, and you can try it yourself. Now I am going to discuss very briefly the properties of determinants. This topic is very important from competitive point of view. We will be discussing all the problems and details of all these properties towards the end of this chapter. Here I will tell you very briefly about some of these properties. First is sum or product of entries of a row with the corresponding entries of the same row. The result will be determinant of A. That is the sum or product of entries of a row with the corresponding entries of the same row. The result is determinant of A. And if the entries of a row are multiplied with corresponding entries of another row and the result is added, the result will be 0. For example, determinant of A is equal to, say, 1, -1, 0, 2, 3, 4 and -2, 1, 6. Now what we do is we first find the cofactors of second row. Cofactors of second row will be, this is first, this is second, the place of this entry is 2, 1. Second row, first column. So first cofactor is A, 2, 1, and since this is an odd place, there will be a negative sign. So minus, and what we get is, now this row is gone, this column is gone. So we are left with -1, 0, 1, 6. We will evaluate directly from here. So we are left with -1, 0, 1, 6. So this into this will be -6 and this into this will be 0. So this will be -6 minus 0. And next is A2, 2. Now A22 is this second row, second column. So this is gone, this is gone. We are left with 1, 0, -2, 6. This is an even place, so we will have a plus sign, and this is second row and second column are gone. We are left with 1, 0, -2, 6. So this will be 1 into 6 minus 2 into 0, that is 0. So this will be 6 minus 0. This will be 6 minus 0. And next is A2, 3. Second row and third column. A21, A22 and A23. So this is an odd place. We will have a negative sign and this will be equal to, this is gone, this is gone. We are left with 1, -1, -2, 1. So this into this will be 1 and this into this will be 2. So 1 minus 2. So this will be 1 minus 2. So this is equal to 6 and this is equal to again 6 and this is equal to 1. Now first we find sum or product of entries of R2 with the corresponding factors of R2. So this is equal to, now entry of R2 is 2 and corresponding cofactor is 6. 2 into 6 plus this entry is 3 and the corresponding cofactor is this. So this will be 6 plus 4 and corresponding cofactor is 1. This. So this is equal to 12 plus 18 plus 4. So what we get is 34. So this is equal to determinant of A. Sum or product of entries of R2 with the corresponding cofactors of R2 is determinant of A. The next is, we now find sum or product of entries of R3 with the corresponding cofactors of R2. Now we are taking entries of R3 and cofactors of R2. So the result must come out to be 0. So let us see. Now entries of R3. First entry of R3 is minus 2 and first cofactor of R2 is 6. Now next entry of R3 is 1 and next cofactor is 6. Second cofactor is 6 plus now next entry of R3 is 6 and the corresponding cofactor is, third cofactor is 1. So this is 1. First entry, first cofactor. Second entry, second cofactor. Third entry, third cofactor. And this should come out to be 0. This is minus 12 plus 6 plus 6. That is 0. So this is what the result states. The property says sum or product of entries of R3 with the corresponding factors of some other row will always be 0. If the rows are different, entries are of a different row and cofactors are of another row, the result will always be 0. The second property is determinant of A transpose. If we interchange the rows and columns of the matrix, we get its transpose. Now determinant of transpose is equal to determinant of A. That is, there is no change in the value of the determinant if the rows and columns of the matrix are interchanged. And third is determinant of A B is equal to determinant of A into determinant of B. That is, if we find the matrix multiplication of A and B first and then find the determinant, or we find the determinant of A separately and determinant of B separately and multiply them, the result will be same. That is, if we carry out matrix multiplication and then find the determinant, or first we find the determinants and then carry out the multiplication, the result will be same. Now next property is, if all entries of a row oblique column of a determinant are 0, value of the determinant is 0. And fifth property is, if a row of a determinant A is a multiple of another row, then value of the determinant is 0. That is, if two rows are multiple of each other, value of the determinant is 0. You need not evaluate. You can directly say, since R1 is 10 times R2, therefore the value of the determinant is 0. Simply by observing, you can say the value is 0. Now next property is, if a row of a determinant is multiplied by a scalar lambda, if any row is multiplied by lambda, the value of the determinant gets multiplied by lambda. In case of matrices, if you multiply a matrix by lambda, all the entries get multiplied by lambda. Now here, if we multiply each and every row by lambda, the value of the determinant will get multiplied by lambda into lambda into lambda in case of a 3 cross 3 determinant. It will get multiplied by lambda thrice. So the difference is, if you multiply a matrix by lambda, you have to multiply each and every entry of the matrix by lambda. And in case of determinant, if you want to multiply a determinant by 2, multiply any row, single row, or any single column by lambda. Now for example, as we did in the last illustration, you can see the slide sheet. Determinant of A came out to be equal to 34. Now what we do is, we multiply the first row by 10. What we get is, we get 10 minus 10, 0, 2, 3, 4, minus 2, 1, 6. Now, if we evaluate this, the value will come out to be 10 times the value of determinant of A. That is 10 times 34. So, we will see this is 10 into, I am expanding it from R1. So 10 into this is gone. We are left with 3, 4, 1, 6 minus, so minus plus 10 into, this is gone, this is gone. We are left with 2, 4 minus 2, 6 plus this will be 0. So this is equal to 10 into 18 minus 4, 18 minus 4 plus 10 into, this will be 12 plus 8, 12 plus 8. So this is equal to 10 into 14 plus 10 into 20. So we get 140 plus 200. That is 340. That is 10 times determinant of A. So what we see is, if we multiply a row of a determinant by 10, its value gets multiplied by 10. Now the next property is, if we add to a row lambda times another row, the value of the determinant remains unchanged. The value remains unchanged. There is no change in the value. If we add to say R1 10 times R2, the value of the determinant will not change. I illustrate it by taking an example. Again, I take up the same determinant which we took in the earlier illustrations. So what we see here is that this was the determinant and we had evaluated, the value was 34. Now what we do is add 5 times R2 to R1. What we get is, now this will be 1 plus 5 times R2. 5 times this is 10, we add this here. So 10 minus 1 plus 5 times this is 15 plus 0 and 5 times of this is 20. So this is 20. And we get 2, 3, 4 minus 2, 1, 6. Now if I evaluate it, we get, this is 11, 14, 20, 2, 3, 4 minus 2, 1, 6. And this is equal to 11 into, now this is gone, this is gone, 3 6 are 18, 18 minus 4 is 14, minus 14 into, this is gone, this is gone, this is 12 minus minus plus, 12 plus 8 is 20, and next is plus 20 into, this is gone, this is gone, 2 plus 6, that is 8, and we get, this is 154 minus 280 plus 160. This is equal to 34. This is equal to 34. You can see the rough calculation. So the value remains unchanged. This is same as the value of the determinant A. Note, if we add or subtract a row from another row, the value of the determinant remains unchanged. This is a direct consequence of this. Lambda equal to 1 will mean we are adding a row to another row, and if lambda is equal to minus 1, this will mean we are adding to a row minus 1 times another row. That is, we are subtracting a row from another row. The last property I am going to take up is thus. Here what we see is this column is sum of these entries and these entries. Sum of these entries. What we do is this determinant will be sum of two determinants. In one of them, this will be the column and rest will remain same, and in the second, this will form the column and the rest will remain same. You can see here, this is same as this is same as this, and this is same as this. Now these two are again same, but in this we are writing only A1 3 dash, A2 3 dash, and A3 3 dash. Now all these properties which are valid for rows also hold for columns. All these properties also hold for columns. That is, say in this, a column of a determinant is a multiple of another column, determinant will be 0. If a column of a determinant is multiplied by a scalar lambda, the value of the determinant gets multiplied by lambda. All the properties hold for columns as well. The next topic I am going to discuss is application of determinants to coordinate geometry. Application of determinants to coordinate geometry. And the first application is how to find area of a triangle using determinants. So first application is area of triangle. Let ABC be any triangle and let A x1 y1 be one of its vertices, B x2 y2 second vertex, and C x3 y3 be the third vertex. Now how to find area of this triangle using determinants? What we do is we define delta equal to half of determinant of, now first vertex is x1 y1. What we write is x1 y1. Second vertex is x2 y2. third vertex is x3, y3, and write 1, 1, 1. Now half the value of this determinant will give us the value of delta. And area of triangle is equal to absolute value of delta. Is absolute value of delta, because area is always positive. So if on evaluation the value of this comes out to be say +3, then area is taken as +3. And if value of this comes out to be -3, we will take the value of the area as +3. Only absolute value is taken. Area is always positive. So we define area as area of triangle is equal to mod of delta. Now if in any question area of triangle is given to be say 5, then we are given that mod of delta is equal to 5, and therefore delta will be equal to ±5. That is, value of this will be taken as ±5, because area is equal to absolute value of this. So if area is given to be 5, absolute value is given to be 5, and value of delta will be ±5. And note, now suppose this point lies here. So I join it with the vertices. Now area of this triangle will be less than the area of this triangle. And further, if we take this point to be here, then what we will see is that area of this smaller triangle is further reduced. And if this point is taken on this line, the area of this triangle will be 0. So if this point lies on this line, area of the triangle will be 0. That is, if area of this triangle is 0, then these 3 points A, B and C will be collinear. Then these 3 points are collinear. That is, they lie on a line. Thus, if area of triangle is equal to 0, then these 3 points will be collinear. Now the next application is to find equation of line through two given points A x1 y1 and B x2 y2. Let Pxy be any general point on the line AB, then the points A, P, B are collinear. And since these 3 points are collinear, area of the triangle formed by them is 0. That is, this will be equal to 0. This means this determinant will be equal to 0. Therefore, first point is x, y, second point is x1, y1, third point is x2, y2. So this determinant must be equal to 0, and this is the required equation of the line. Now I will take up some applications of these two formulae. First question is, find the equation of the line joining 1, 3 and B 0 using determinants, and find K if dk0 is a point such that area of the triangle ABD is 3 square units. We are given 2 points A13 and B00. Equation of line through AB is xy1, x1, y1, 1, x2, y2, 1 is equal to 0. You can see the side sheet. So here the points are, this is the general point x, y, 1, and the first point is 1, 3. So the x1 is 1, y1 is 3, and this is 1. Second point is 0. This is 0, this is 0, and this is 1. This equal to 0. And on expansion, what we get is x into. Now we expand this determinant from the first row. So what we get is x into its cofactor. So we delete this row and this column and we get 3, 1, 0, 1. On expansion, this is 3 minus 0. 3 minus 0. I am directly expanding the determinant as we have now got a lot of practice. So this will be, now this will be negative. This is gone, this is gone. So we are left with 1, 1, 0, 1. So 1 into 1 is 1 minus 0. This is 1 minus 0. Again, this would be 1 positive into its cofactors. So this is gone, this is gone. We are left with 1, 3, 0, 0. So this will be 0 minus 0. 0 minus 0 is equal to 0. So what we get is 3x, this is 3, and this is y, and this is 0. 3x minus 0. This is the required equation of line. Now, first part of the problem is answered. Find the equation of the line joining these 2 points. Now, the second is using determinants, find k if dk 0 is a point such that the area of this triangle is 3 square units. Now, second part is area of triangle. Area of triangle ABD is equal to 3 square units. And we have to find K. So, area of this triangle is 3. Therefore, half of area of triangle is x1, y1, 1, x2, y2, 1, x3, y3, 1. You can see the side sheet. First point is 1, 3. So we get 1, 3, 1. Second point is 0, 0. So we get 0, 0, 1. And the third point is dk0. So what we get is k0, 1. So this must be equal to 3 square units. So this must be plus minus 3, because even if this determinant, the area comes out to be minus 3, it is taken as 3. And if it is 3, we take it 3. This may give the value as plus or minus, but we have to take the absolute value of the area. So in such questions we take plus minus 3. So this implies this is equal to half into. Now to expand this matrix, what we prefer is we expand this determinant from the row or column in which maximum number of zeros occur, because this will be the shortest. How? Because if I say expand it from here, there are 2 zeros in this. So what we will get to is 3 into its cofactor, and this will be 0 into its cofactor. We need not find the cofactor. And here also it is 0. We need not find the cofactor. So place of this entry is 1, 2. 1 plus 2 is odd. So we will get minus 3 into its cofactor. So this is gone and this is gone. So we are left with 0, 1, k1. So 0, 1, k1. So this will be 0 minus k. This will be 0 minus k, and this is 0, this is 0. This determinant is evaluated. So you should always prefer the row or column in which maximum number of zeros occur. Expand the determinant from that row or column. So this will be equal to plus minus 3. So this implies this will be plus 3. This is 3 by 2. So we take this 2 to other side. So what we get is 3k is equal to plus minus 6. 3k is equal to plus minus 6. That is k is equal to plus minus 2. So there are 2 points D from which the area of this triangle can be 3 square units. That is, there are 2 points D, K, 2, 0 and D minus 2, 0. The situation is, for example, I plot these points. This is 0, 0 and 1, 3. So say this is 1 and 3 times this on the y-axis. 1, 2, 3. So this will be the point 1, 3 approximately. So this will be the point A, and the point D is minus 2, 0. So minus 2, 0. Minus 2 and 0. This is the point. So this is the triangle with area equal to 3. Now the second triangle is, this point is D20. This is D minus 20 and D20. So D20 is 1 and 2 here. This point will be D20. So what we get is this triangle. So this is the point. If I say this is D1 and this is D2, then this will be D1 and this will be D2, and area of both these triangles will be equal to 3 square units. A is given to be 1, 3. 1, 3. So this is approximately 1, 3. So A is 1, 3, B is given to be 0, 0, and D1 point is 2, 0. D1 point is 2, 0, and D2 point is minus 2, 0. So we are getting these two triangles. Now how is the area of these two triangles equal? Now I will show that area of this triangle and this triangle is 3 square units. Now let us draw a perpendicular from this vertex. This is the perpendicular. Now length of this perpendicular is 3. This is 1, this is 3, because A is 1, 3. X coordinate is 1 and Y coordinate is 3. So this is 3. Now this is 2, 0. So this length is 2. Base is 2. And this is minus 2, 0. So this is 2. So area of this triangle will be half base into altitude. Area is half base. Base is 2 into perpendicular. Perpendicular is 3. So these two cancels and we get the area as 3. And same, because perpendicular is again for this triangle, perpendicular is 3 units and base is 2 units. So we get the same area. This is why we are getting 2 points D1 and D2. Because these 2 points will form triangles, each of which has area 3 square units. Now next question is, find the area of the triangle with vertices this, this and this. Are these points collinear? Now this is a very simple question. You can directly apply the formula for area of triangle and find it. If the area comes out to be 0, then the points will be collinear. And if area is non-zero, then the points are non-collinear. You can try this question yourself. The next question is, using determinants, prove that the points this are collinear. If AB dash is equal to A dash B. Now, we are given that the points this are collinear. Therefore, the determinant x1, y1, 1, x2, y2, 1 and x3, y3, 1 should be equal to 0. Now, the first point is AB. So, we take AB 1. Next point is A dash, B dash 1 and A minus A dash, B minus B dash and 1 must be equal to 0 because given points are collinear. So this determinant must be equal to 0. Now we expand it from say R1. So what we get is A into, now this row is gone, this column is gone. We are left with B dash 1, B minus B dash 1. So this into this is B dash minus 1 into this is B dash, this into this is 1 into B minus B dash. Now next, this is an odd place of this entry is 1, 2. So 1 plus 2 is odd. So we get minus B into. Now this is gone, this is gone. We are left with A dash 1, A minus A dash 1. So what we get is A dash into 1 is A dash minus. This into this is 1 into A minus A dash. And the next entry is 1. Place of this is, or we can say this is plus, this will be negative, this will again be positive. In place of this entry is 1, 3. 1, 3. First row and third column. 1 plus 3 is 4, so even place. So this is gone, and we are left with now this is gone, we are left with A dash into B minus B dash, this into this minus this into this, minus B dash into A minus A dash. This must be equal to 0. Now on simplification we get this is B dash minus B plus B dash. B dash minus B plus B dash. So what we get is A into, this will be 2B dash minus B minus B into, this will be equal to A dash minus A plus A dash. So this will be 2A dash minus A plus 1 into, this will be A dash B minus A dash B dash minus B dash A minus plus A dash B dash. So this must be 0. These two cancel and we get 2AB dash minus AB minus 2BA dash minus plus AB and plus A dash B minus b dash a is equal to 0. Now 2ab dash, ab dash. So we are left with ab dash, 2ab dash minus this ab dash. So we are left with ab dash, and this cancels with this, and we have 2ba dash, 2ba dash and ba dash. We are left with minus ba dash. This is equal to 0, and if ab dash is equal to ba dash, hence proved. This was the result to be proved. Now the next question is, a triangle has its three sides A, B and C. If the coordinates of its vertices are ax1, y1, ax2, y2 and cx3, y3, show that this determinant is equal to a plus b plus c into this. So what we do is, we write left hand side is equal to, this is left hand side, and we can write this as, while doing the properties of determinants, what we learned is, if we multiply a determinant by 2, only one row will get, or one column will get multiplied by 2. So if we want to multiply a determinant by 2, we multiply a single column. So in order to take common from a determinant, we can take common from a single column. So this will be 2 will come out, and we will be left with x1, y1, 1, x2, y2, 1, x3, y3, 1 whole square. Now here what we see is, if we want to multiply this determinant by 2, I will multiply any one row or any one column by 2. So here we multiply the column C3 by 2. So multiply this column by 2. What we get is, we will get 2, 2, 2. So we get this determinant. This will be equal to 2 square. 2 square will be common, and what we get is determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. And this whole square. What we do is, we divide here by 2. So in order to adjust it, we will have to multiply square. So 2 square will cancel, and we get this back. So what we get here is, this is equal to 2 2s are 4, 4 4s are 16, and this is nothing but area of the triangle joining these 3 points, x1, y1, x2, y2, x3, y3. So this is this delta square, 16 delta square. Now in this question, the question was mainly of interpretation. What does this determinant on the left hand side mean? What we did is, this was the left hand side. We took 2 common, and then what we did is, we got this determinant. We divided it by 2 and multiplied it by 2. So what we get is, this left hand side is equal to 16 into area of the triangle. So this side is nothing but 16 times area of the triangle square. 16 into, now by Hero's formula, area of the triangle is S into S minus A into S minus B into S minus C. And S is nothing but a semi-perimeter. So S is equal to half A plus B plus C. Now, by Hero's formula, area of the triangle is under root of this. So, since we are having delta square, so here it will be S into S minus A into S minus B into S minus C. So, this is equal to 16 into. This will be A plus B plus C by 2 into A plus B plus C by 2 minus A into A plus B plus C by 2 minus B into A plus B plus C by 2 minus C. And this on simplification gives 16 times A plus B plus C by 2 into, now LCM is 2. What we get is A plus B plus C minus 2A. And this will be A plus B plus C minus 2B by 2. And this will be A plus B plus C minus 2C by 2. And this is equal to 2 2s are 4, 2s are 8, 2s are 16. So 16 cancels with 16. And we are left with A plus B plus C into. This will be B plus C minus A. This will be A minus B plus C. And this on simplification gives A plus B minus C. So this is the answer. This is equal to RHS. Hence proved.